Hi, good day to everyone. I'm Christian F. Capsa, a student at Mapua University with a bachelor's degree in bioengineering. Today, I will be presenting my undergrad thesis entitled Fabrication and Characterization of Polylactic Acid Incorporated with Hydroxylated Halocite, shortened as PLA-HHNT composite fiber mass for wound dressing applications via electrospinning. My thesis advisor for this study is Ma'am Ruth R. Aquino. So the fabricated e-spun or electrospun fiber mat looks like this under the naked eye. But upon closer look under scanning electron microscope, you can see the fiber morphology of the material. First, let's go over to a brief introduction of this study. Our body has a self-repairing mechanism, which means it can heal wounds by itself, right? Quite often, however, depending on the severity of the injury, as you can see in the pictures, immediate medical care is required. This issue can emphasize the importance of an appropriate wound dressing. The basic function of wound dressings used in their care remains the same. It acts as a temporary barrier to cover the wound. Listed here are the standards for wound dressings. So with these standards as the basis or point of comparison, we can create or fabricate novel dressings made from biomaterials. One technology that has recently been established is electrospinning. As you can see in this illustration, this is a conventional electrospinning setup consists of a syringe containing the polymer solution, a single nozzle, which is the metallic needle, a power supply, and a grounded collector plate. So a strong electric field or high voltage is applied between the needle and the collector plate. The polymer solution is pumped through the needle, and an electrified pendant-shaped droplet of polymer solution emerges from the tip of the needle, then deforms into a conical shape known as a Taylor cone. Then a thin polymer jet stream will shoot out and lands on the collector plate. It is therefore a process of utilizing electrostatic forces capable of producing fine polymer fibers in the micro to nano diameter range. So we also have here an illustration of the desired properties when fiber mats are applied on skin wounds. Okay. Next are the materials used in the study. We have here polylactic acid or PLA and hydroxylated halocite or HHNT. PLA is a biodegradable polymer, FDA approved for biological fluids, also easily electrospun provided that the polymer has high solubility with a solvent, and there are many literatures citing the use of PLA for electrospinning. Then we have halocite. A clay mineral consists of 1:1 aluminosilicate layer rolled into tubular structures. Halocite has been studied as an additive or reinforcement material for PLA, and that is also true in the study. However, it will be treated with mild alkaline solution, which is the novelty of the study in order to enhance the density of hydroxyl groups on the external surface of HNTs, thus leading to a much higher degree of dispersion and interfacial interaction of HNTs in polar solvents and polymer matrices. The main objectives of this study was to fabricate PLA fibers with different concentrations of HHNT electrospun in DCM-DMF mixed solvent system. Even though many researchers claim that the electrospinning technology can almost use every type of polymer out there, it doesn't guarantee the quality and quantity of the produced e-spun material with regards to its potential as a wound dressing. Which brings me to my next objective, that is to investigate and evaluate the physical, mechanical, and biological properties of the spun material. However, as you can see, the characterization for biological properties crossed out. It should be included when I had my thesis proposal. However, due to the lockdown of schools and the pandemic, I had to stop and make use of what I have already gathered and accomplish the paper. Okay? That said, the scope of my study is only limited to the effect of the different hydroxylated halocite content on the fiber mat's morphology, its mechanical strength, surface wettability, and porosity. With these tests, we can identify which of the three concentrations of hydroxylated halocite enhances the property of the e-spun PLA fiber. We now move on to the methodology of this research. We have here the materials for the electrospinning process. PLA serves as the polymer matrix. Then this fine white powder here is the halocite clay mineral, the additive which was treated first with mild alkaline solution. So we have sodium hydroxide for that. And lastly, the solvents to make up the polymer solution, dichloromethane and dimethylformamide, or DCM and DMF for short. These two solvents were used based on literature. The first thing to do is to prepare the hydroxylated halocite. So in a 100 ml deionized water, 2 grams of halocite was added with mild stirring. Afterward, 0.01 molar NaOH was added into the solution. Then magnetically stirred for 24 hours at room temperature. As you can see, the alkaline solution is only at 0.01 molar. If a stronger alkaline solution was used, the tubular morphology of HNT was said to be destroyed, according to a journal article. Okay. Also, in this step, the siloxane moieties present in the surface of HNT undergoes hydrolysis to form reactive silanol groups. The resultant HNT solid phase was separated by centrifugation and rinsed several times with deionized water until pH was 7. The prepared HHNTs were dried at 120 degrees Celsius in an oven for 12 hours and stored in a desiccator until it was used. Also, to confirm whether the HNTs have been properly treated after it has dried, a sample should be taken for FTIR analysis. Okay. Next step is the preparation of polymer solutions. So pure PLA solution was carried out by dissolving PLA resins with a 12 weight % concentration in 3:1 DCM-BMF mixed solvent system for about 2 hours at room temperature and then electrospun. For PLA HHNT composite solutions, on the other hand, PLA resin was first dissolved in 3 parts of DCM solvent, or 75% of the solution, followed by mixing the prepared HHNTs of varying concentrations in 1 part DMF, or 25% of the solution. The 3 concentrations of HNTs, by the way, are 0.5%, 1%, and 3%. Okay, so now the 2 solutions were added together and sonicated for about 20 minutes to homogenize the solution, and it can be transferred into the syringe and electrospun to produce the fibrous material. I also have here a table showing the composition of solution blends for electrospinning. The values represented here uses 100% as a basis. All right. As for the electrospinning process, these are the operation conditions or process parameters. The prepared homogeneous solution was transferred in a 5 ml plastic syringe with 21 gauge blunt tip needle. The voltage was set to 20 kilovolts and a varying flow rate of 0.8 and 1 ml per hour was employed because sometimes the polymer jet dries up at 1 ml per hour and solidifies at the needle tip and would produce this continuous stream over time. Each solution undergoes electrospinning over a course of about 4 hours. So shown here is the setup in the vertical configuration. The electrified polymer solution travels from the needle tip to the collector plate with aluminum foil. The deposited fibrous mats were dried under atmospheric pressure at room temperature and carefully detached from the aluminum foil for characterization tests. So this is a list of the tests done, alright, and included here are most of the equipments or instruments used for characterization. Let's now head over to the results and discussion. Included in the results are the following. First, we have here the absorbance spectra of halloysite before and after hydroxylation. There are 2 strong peaks here at these wave numbers. They can be attributed to the external surface consisting of a single bond stretching between silicon and oxygen molecules, and a bond stretch of the inner surface hydroxyl groups, also called aluminal groups, okay? Observed at higher wave numbers, around 3600, are also 2 strong peaks, which correspond to the stretching vibrations of the oxygen-hydrogen bond in the inner surface of the halloysite's tubular structures. After mild hydroxylation, the characteristic peaks for halloysite are still there, so we can say that the tubular structure was maintained. There were a few small absorbance peaks discovered here, which is near the siloxane peak, so this may indicate a change in the bond stretch of silicon and oxygen molecules. Moving on to the characterization of fiber mats. Looking more closely using a scanning electron microscope, results show thin bead-free fiber structures in randomly oriented formations. So the production of PLA fibers was obtained at 12.8%, which was also used as the basis for clay content. Varying concentrations of hydroxylated halloysite were successfully electrospun into fiber mats. So I have included here images captured using camera lens. Zooming in, when I peel this off the aluminum foil, you can see microfiber strands. This is for pure PLA only. And then for the PLA HHNT composite fiber mats, the fibers are not that observed and they have a much firmer structure compared to this one. And as you can see, they're not peeled off totally from the foil, maybe because of the electric charge between the foil and the fiber mats, which keeps the fiber mats attached to the foil. So looking at the fiber diameter, as you can see, fiber diameters reported here are shown as a ranged value because the determination of each fiber's diameter was done manually. But it was observed that increasing HHNT content slightly decreases the mean average diameter of the composite fiber mats. Also, fiber morphology for pure PLA was observed to be smooth and densely packed. This may be due to the use of a conductive collector, which helped dissipate the charges and reduce the repulsion between fibers. On the other hand, the morphology of the polymer clay composite membranes was observed to have a slightly rougher, uneven surface with improved diameter uniformity. This may have been due to the increase in viscosity of the polymer solution, which affects the stream jet spin and results in increased fiber cohesion points. Incorporation of the clay in the polymer matrix has caused the fibers to have branching orientations, which may also affect the mechanical properties of the membrane. So next is the FTIR analysis of PLA and the composite fiber mats. So for the polymer matrix, characteristic peaks at 2995 and 2945 wave numbers can be attributed to a carbon-hydrogen bond stretch, while a strong peak captured at 1748 can be attributed to the carbonyl bond stretch of an ester. The intensity of the signal represents the strong dipole moment associated with the carbonyl of PLA. At increasing clay content, a broad signal was observed at around 3200, which indicates the presence of oxygen-hydrogen bonding. This in turn has affected the signal of the carbonyl bond stretch for PLA. The intensity of the carbon-oxygen double bond was observed to decrease at 1% HHNT and 3% HHNT, which may indicate a weakening of the dipole moment due to formation of OH bonding. It is suggested that the incorporation of a higher concentration of HHNTs affected the strong peak signals at 2995 and 2945 wave numbers originally detected in the PLA spectrum. A band shift was also observed for 1% and 3% PLA HHNT fiber composites at 626 and 632, which are associated with the formation of silicon-oxygen-aluminum bond stretch of halloysite. So these findings could be attributed to the bonding interactions between PLA and HHNTs. So let's now investigate and evaluate the effect of HHNT to the mechanical property of the electrospun polymer matrix. So on the x-axis are the samples, pure PLA, and 3 different concentrations of HHNT. In this first line graph, the sample with the highest tensile strength is at 1% HHNT, while the lowest is at 3% HHNT content. So this is the force responsible for the stretching of the material. How long the material is stretched is also plotted here. Results show that pure PLA has the highest elongation and then it decreases with increasing HHNT content. What this means is that we go from an elastic material to a stiffer or less elastic material. And then the third graph is the stress-strain curve to measure the elastic modulus of the samples. 0.5% and 1% HHNT content has the highest modulus. And then at 3% HHNT content, the electrospun fiber mat has low tensile strength and modulus. Also shown here, this may be due to the formation of clay agglomerates being a source of weak points resulting in reduced mechanical performance, as observed in other papers. So a wound dressing material needs sufficient tensile strength and elastic property to withstand stresses exerted by body parts. Hence, tensile strength and modulus can be connected to the conformability of the wound dressing material. The tensile strength and modulus of 1% HHNT content were observed to be the highest and most favorable reinforcement for the polymer matrix. Hence, the reinforcement of hydroxylated halcite slightly enhances tensile strength and modulus initially at 0.5% and 1%. And then diminishes as clay content decrease. The hydroxylated HNTs may not have been enough to be completely dispersed into the polymer matrix, resulting in increased rigidity of the composite fiber mass in poor mechanical property, as what's seen at 3% HHNT content. Next is the surface wettability of electrospun fiber mats. So the average water contact angle was recorded. The electrospun PLA sample, known to be a hydrophobic synthetic polymer due to a lack of polar functional groups, exhibited a water contact angle of 110.6 degrees. The effect of increasing HHNT content on the polymer matrix resulted in a slight decrease in contact angle. However, since the measured contact angles for the electrospun fiber mats are greater than 90 degrees, the wettability of the mats indicates a hydrophobic surface. So next is assessing the pore size of electrospun composite mats, which connects to the material's air permeability. An increase of HHNT content revealed increasing pore sizes. Mean flow pore sizes of 3 to 6 micrometer may provide breathability at the wound site, allowing oxygen molecules to pass through the electrospun fiber mat. Okay, as you can see here, at 1% HHNT content, it has the lowest mean pore size, and its smallest pore size is also 1.8 micrometers. The smaller the pore size, the better, so that it can also block harmful microorganisms from entering the wound bed. The average size of most bacteria, however, is between 0.2 and 2 micrometer in diameter. So for this material, PLA with 1% HHNT content, it is only partially effective as a barrier to prevent microorganisms from entering the wound site. All right, so in conclusion, halcite nanotubes were treated with a mild alkaline solution to enhance the density of hydroxyl groups on the external surface of HNTs for better dispersion and interfacial interaction with the polymer matrix, and it was confirmed. 3 different concentrations of the treated HNTs were incorporated into PLA solutions and successfully electrospun. So the fiber morphology of the pure and composite fiber mats was good. So some images showed bead-free fiber structures in randomly oriented formations, which was also desired in many published papers. And FDIR results also revealed successful interfacial interaction between the hydroxylated clay and the polymer matrix. At 1% and 3% HHNT content, the chemical interactions were more evident compared to 0.5%. Consequently, the reinforcement of low HHNT concentration, less than or equal to 1%, into the polymer matrix improved tensile strength and modulus compared with pristine or pure PLA. So we can say that the conformability is good at 1% HHNT content. However, increasing HHNT content further decreases the elasticity of the fiber mat, which may hinder the conformability of the material when applied to the wound surface subject to movement. Okay. As for the material surface wettability, its contact angle is more than 90 degrees, so the material is hydrophobic. So it does not address the absorbency property of a wound dressing. It was also concluded that the hydroxylation of the nanotubes has little significance to the overall wettability of the composite fiber mats. However, the waterproofness property of a dressing can be addressed if the fabricated material is used as an outer layer in contact with the environment, protecting the wound from foreign liquids. So it can be for waterproofness. Due to the porous nature of the e-spun material, it can allow air to pass through to give breathability to the wound surface. But it is still limited as it cannot absorb excess wound exudates, and it cannot totally block out all microorganisms due to its bigger pore sizes, or it can only partially block those microorganisms out. So although the fabricated PLA HHNT composite mats did not possess sufficient properties as a wound dressing, data shown here have significant importance that can aid to further tune the properties of fibrous biomaterials. Recommendations to further improve this study are as follows. It is recommended to use TEM or transmission electron microscope for a better observation of the employed modifications on halcite nanotubes. Incorporating antibacterial agents into the polymer solution or designing a novel method of functionalizing the outer surface of HNTs with bioactive agents can be explored in the future. It is also recommended that additional tests for the biocompatibility of the PLA HHNT fiber mat should be made. The simplest would be in vitro analysis using SBF solution at 37 degrees Celsius for 7 days. So that ends my presentation. Thank you for listening, and God bless us all.